Hello everyone and welcome back to my channel. I am Aad Fataya and today we are continuing our exciting journey into the world of AI Research Agent. We are at episode 4 where we will transform our raw data into an intelligent knowledge base that will power our research assistant. But wait, I know 2024 has been the year with the highest employment rates and even higher layoffs. Even in 2025, it started with the same layoff rate. And even if you have a well-paying job today, you could be jobless tomorrow. This is scary, right? But relax. Let me tell you there's a way to protect yourself and your family, which is by building multiple passive income streams. I'm talking about learning and using AI as a skill to earn an extra $10,000 every month. I know who can help you here. Gross School is offering 3 hours on AI training, where they teach you how to use over 25 AI tools. Register now, the link is in the description. Trust me, this training is a game changer for people who want to grow in their career. And here's the best part. This is normally paid training, but it is exclusively free for the first 1,000 Atif Ataya viewers who join using the link below. Yes, for free. Only for my channel viewers. People who register will receive a free $500 bonus worth of extra resources. It covers everything from job hunting strategies and salary negotiation techniques to mastering Excel and creating content. This AI training isn't just for tech folks. Whether you are in finance, sales, marketing, HR, a student, or an entrepreneur, this training is definitely for you. Gross School has helped over 1 million people upskill across the globe. And this is your chance to join the top 1% in an AI first world. So click the link in the description, snag your free spot, and this is your only chance to learn those skills that will secure your future. Don't forget to join Gross School's WhatsApp community to not miss any updates and meet other AI lovers just like you. Now, let's get back to our AI Research Agent series, where we will build something that will truly transform the way we interact with research data. Before we start, let's recap what we have covered so far. In episode 1, we laid the foundation for our project. We discussed what AI Research Agent is and how it can transform the way we process and understand academic papers. We outlined our 6-episode roadmap and introduced key technologies that we will be using throughout this series. In episode 2, we got our hands dirty with code. We set up our environment with all the necessary libraries and learn about arXiv, a goldmine of academic research papers. We wrote a Python function to extract data from arXiv, allowing us to fetch academic research paper based on specific queries. This gave us the raw material we need for our AI agent. In episode 3, we built what I like to call the brain of our AI agent. We created a system that can process PDFs of research paper, break them into meaningful chunks, transform these chunks into mathematical pattern called embedding, and store them into Pinecone, our specialized vector database. This transforms our data from a human-readable text into a format that allows our AI to understand and connect ideas through thousands of research papers. Now, in episode 4, we are going to bring everything together by building powerful search tools that allow our AI agent to retrieve and process knowledge effectively. We are essentially giving our agent the ability to think using the data we have processed. Let's dive in. Today's episode is especially exciting because we are going to see our research agent start to take shape. We have collected our data, we have processed it, and now we are going to build the mechanism that allow our agent to access and leverage this knowledge. In today's episode, we will focus on creating 3 key components. First, we will implement specialized tools for our agent to access different sources of information. including our Pinecone vector database, the arXiv API, and Google search results through SerpAPI. Second, we will create a decision-making system using LangGraph that will intelligently choose which tools to use based on the user query. Finally, we will develop a report generation framework that will present the research finding in a clear, well-structured format. By the end of today's episode, you will have a fully functional AI research agent that can answer complex questions by drawing on multiple sources of information. This is where our hard work starts to pay off, and I can't wait to show you the result. Let's dive into the code and start building these powerful search capabilities. First, let's build a tool that allows our agent to fetch information from arXiv directly. This is incredibly valuable because it allows our agent to access up-to-date academic research paper abstract on demand. The great thing about this tool is that even if we haven't stored information about a particular academic research paper in our Pinecone database, our agent can still retrieve information by querying arXiv directly. Let me show you how to build this tool, and then we will test it to make sure it works correctly. Let me show you how we can fetch information from arXiv. First, we need to import the request library. This is what allows us to make HTTP requests to websites from our Python code. Now we will set up a variable called arXiv_ID that contains a unique identifier for a specific research paper. In this case, I'm using 2502.20384, which is the ID for a paper I want to retrieve. Next, we use the request library to make a GET request to the arXiv website. See how I am using an f-string to build the URL. We are basically telling our code to visit arXiv followed by the paper ID we specified. When we execute this line, our code reaches out to arXiv server and downloads the web page for that paper. We store the response in a variable called res. Finally, with res.text, we are accessing the actual HTML content of the web page. This gives us the raw HTML as a string, which contains all the information about the paper, but it's not very readable yet because it includes all the HTML markup. Let's run the code cell now. Now that we have the HTML content of the arXiv page, we need to extract just the abstract of the paper. This is where regular expressions come in handy. First, we import the RE module, which is Python built-in regular expression library. Regular expressions are powerful patterns that help us search through text. Next, we are creating a pattern called abstract pattern that will specifically look for the abstract section in the HTML. Let me break down what this pattern is doing. We are looking for a block code element with the classes abstract and mass JAX. Inside that, we expect to find a span with the class descriptor containing the text abstract. What we really want is whatever text comes after this span, that's our abstract. The parentheses in the pattern create a capturing group that will grab just the abstract text. The RE flag is important because it allows our pattern to match across multiple lines, which is necessary since abstracts typically span several lines. Then we use the search method to look for this pattern in our HTML content. If we find a match, it gets stored in the re_match variable. Finally, we check if we found a match. If we did, we print just the content of the first capturing group, which is our abstract text, using group 1. If no match found, we simply print abstract not found. This technique of using regular expression to extract specific information from web pages is called web scraping, and it's incredibly useful when working with scientific literature or any structured data on the web. Let's run the code cell now, and we get the abstract. Now let's take what we have learned and package it into a reusable tool for our agent. First, we are importing the tool decorator from the langchain_core.tools module. This decorator will transform our function into a tool that our agent can use. We are also importing the same libraries we used earlier, request for making HTTP calls and RE for regular expression. And we are defining our abstract pattern again, just like before. Now here's where it gets interesting. We define a function called fetch_arXiv and decorate it with add tool, giving it the name fetch_arXiv. This tells LangChain that this function is a tool our agent can call. Our function takes one parameter, the arXiv_id, which is the unique identifier for the paper we want to retrieve. Notice how we have added type hints here. arXiv_id string means this parameter should be a string, and str means our function will return a string. We have also added a detailed docstring that explains what the function does, what argument it takes, and what it returns. This is crucial because our agent will read this docstring to understand when and how to use this tool. Inside the function, we are doing exactly what we did earlier, making a GET request to the arXiv website for the specific paper, searching for the abstract pattern in the HTML, and returning either the abstract text or an error message if it's not found. The key difference is that now instead of printing the result, we are returning it. This allows our agent to capture the output and use it in its reasoning process. What we have done here is create a specialized tool that gives our agent the ability to access scientific papers from arXiv. This is just one of many tools we will create to expand our agent capabilities. Let's run the code cell and make sure everything is working fine. Now that we have created our fetch_arXiv tool, let's test it out to make sure it works correctly. First, I'm defining a variable called arXiv_id and assigning it the string of the paper. This is a unique identifier for a specific research paper we want to retrieve from arXiv. Next, we need to call our tool. But notice that we don't call it like a regular function. Instead, we use the .invoke method. This is because our function is now a LangChain tool, and tools are invoked rather than called directly. When we invoke the tool, we need to pass the parameters as dictionary. That's why I'm using input equal arXiv_id colon arXiv_id. The key arXiv_id matches the parameter name in our function, and the value is the variable we defined above. After invoking the tool, it will execute all the code inside our function, makes the HTTP request, extracts the abstract, and returns the result. We capture this result in the output variable. Finally, we print the output to see the abstract of the paper. This is just for our testing purposes when our agent uses this tool. It will work with the return text directly rather than printing it. This pattern of defining a tool and invoking it is fundamental to how we will build our research agent. Each tool provides a specific capability, and the agent will decide when to invoke each one based on the user's query. Now that we have our arXiv fetch tool, let's expand our agent capabilities by implementing a web search tool. This will allow our agent to gather information from the broader internet, not just academic paper. For this, we will use SerpAPI, which provides a clean interface to Google search result. This tool will be especially useful for gathering general knowledge or recent information that might not be available in academic papers. Let me show you how to set up and use SerpAPI in our agent. Now let's move on to creating our second tool, one that will allow our agent to search the web using Google. This is crucial because it gives our agent access to up-to-date information from across the internet. First, we need to import some libraries. We are using .env to load environment variables, which is a secure way to store API keys. The load_.env and find.env functions help us locate and load variable from a .env file. Next, we import Google Search class from the SerpAPI library. SerpAPI is a service that allows us to make Google search queries. We also import OS for accessing environment variables and getPass, which lets us securely input password or API keys. Now let's set up our search parameter. We create a dictionary called SerpAPI_params with two key pieces of information: the search engine we want to use, which is Google, and our API key. Notice how we are getting the API key. We first try to retrieve it from the environment variable using os.getEnv. And if that fails, we prompt the user to enter it securely using getPath. This is a best practice for handling sensitive information like API keys. Next, we create a Google search object passing in our parameters along with the search query water and specifying we want 5 results with the num parameter. The double asterisk syntax SerpAPI underscore params is a Python feature that unpacks our dictionary into the larger dictionary. After performing the search, we extract just the organic result from the response using get underscore dict followed by get. This gives us a list of result items. Finally, we format this result into a readable string. We are using a list comprehension to extract the title, snippet, and link from each result, joining them with new lines, and then joining all the result with a separator line. When we print the formatted result, we get a clean readable output of the top 5 Google search result for water. Let's run the code cell now. We hit an error here. This is actually a common issue when working with external libraries. The error message module not found error, no module named SerpAPI tell us that Python cannot find the SerpAPI library that we are trying to import. Before we can use any external library, we need to install it first. For SerpAPI, we need to run a pip install command in our terminal or notebook. Let's fix this by installing the required package. You would typically run this command -q. Let's run the code cell. This might seem confusing because we are importing SerpAPI but installing Google search results. That's because the actual package name is Google search result, but it provides the SerpAPI module. Let's run the code cell again. And we get the result. This will be incredibly useful for our agent to find relevant information based on user queries. Now that we have installed the SerpAPI library, let's package our Google search functionality into a tool that our agent can use, just like we did with the arXiv tool. First, we import the Google search class from the SerpAPI module that we just installed. Next, we define our web search function and decorate it with add tool, giving it the name web_search. This transforms our function into a tool that our agent can call when it needs to search the web. Our function takes one parameter, query, which is the search term the agent wants to look up. Notice the type hints again. Query should be string, means this parameter should be a string, and the function will return a string as well. The duck string is crucial because here it tells our agent what this tool does and when to use it. We explain that it finds general knowledge information using Google search, what arguments it needs, and what it returns. Inside the function, we create a Google search object, passing in our previously defined SerpAPI underscore params along with the query and limiting the result to 5. Then we extract and format the result just like we did before, joining them into a readable string. Finally, we return either the formatted results or no results found message if the search didn't yield any result. Let's run the code cell now. To test our tool, we invoke it with the query water on Mars. Notice we are using the same .invoke method pattern, passing parameters as the dictionary with the key matching our function parameter name. When we run this code, our tool will make a Google search for waters on Mars, format the top 5 results, and print them out. This gives our agents the ability to find up-to-date information about virtually any topic a user might ask about. This web search capability complements our arXiv tool nicely. The arXiv tool helps with the specific scientific papers, while the web search tool provides broader general knowledge. Together, they give our agent a much richer set of information sources to work with. Now we are going to implement the most important search capability, the ability to search our Pinecone vector database through natural language query. This is what makes our agent truly intelligent. It understands the meaning behind the query and retrieves relevant information even if the query contains words different than those in the academic research paper. This approach is called Retrieval-Augmented Generation, or RAG, and it is at the heart of modern AI research assistant. Let me show you how to implement these RAG tools for our AI agent. Now we are moving into the third component of our system, Retrieval-Augmented Generation, or RAG. This is where we connect our agent to a vector database that stores chunks of scientific papers. Let's start by creating a helper function called format_rag_context. This function will take the raw result from our vector database and turn them into a readable format for our agent. This function takes one parameter called matches, which is a list of document matches returned from our vector database search. Each match contains the text, content, plus metadata where it came from. Inside the function, we first create an empty list called formatted_results that will store our formatted strings. Then we loop through each match in the list and extract the important metadata. For each match, we create a formatted string that includes the title of the paper, the specific chunk or passage that matches the query, and the arXiv ID of the paper. Notice how we are using fstring again. They are really handy for creating formatted text with variable embedded directly in the string. After formatting each match, we append it to our results list. Once we have processed all matches, we join them together with a separator line to create one big string that contains all our formatted results. This function is important because it transforms raw database results into a format that's both human readable and useful for our large language model to process. When our agent retrieves information from the vector database, it will use this function to format the result before analyzing them. RAG is powerful because it allows our agent to access specific information from a large corpus of documents without having to memorize everything. It's like giving our agent the ability to quickly look up relevant information in a specialized library. Let's run the code cell now. Now let's create our first RAG search tool. This one will allow our agent to search for information within a specific paper in our vector database. First, we import the add tool decorator from langchain_core.tools, just like we did for our previous tools. Notice that this time we are not specifying a name for the tool. When we don't provide a name, LangChain will use the function name as the tool name. We define a function called rag_search_filter that takes two parameters, query, which is the natural language question we want to answer, and arXiv_ID, which is the specific arXiv paper we want to search within. The doc string explains that this tool finds information from our arXiv database using a natural language query, but limits the search to a specific paper. This is useful when our agent already knows which paper contains relevant information and wants to dig deeper into it. Inside the function, we first encode our query into a vector representation using an encoder model. This transforms the natural language query into a numerical vector that can be compared with the vectors in our database. Next, we perform a search on our Pinecone vector index. We pass in the query vector, specify that we want the top 6 most relevant results, include metadata with each result, and most important, we add a filter to only return matches from the specific arXiv ID that was provided. Finally, we format the search results using our format_rag_context function that we just created and return them. This tool gives our agent the ability to do targeted searches within specific scientific papers. For example, if a user asks about a particular aspect of a paper, our agent can use this tool to find the most relevant sections without having to search through the entire database. This makes our agent much more efficient at retrieving specific information. The beauty of vector search is that it finds semantically similar content, not just exact keyword matches, so our agent can find relevant information even when the question is phrased differently from the text in the paper. Let's run the code cell now. Now let's create our second RAG search tool, which is a bit more general than the first one. This tool will allow our agent to search across all papers in our vector database, not just a specific one. We define a function called RAG_search and decorate it with add tool, explicitly naming it RAG_search. This is the tool our agent will use when it needs to find specialist information but doesn't know which specific paper to look in. Our function takes just one parameter query, which is the natural language question we want to answer. Since we are searching across all papers, we don't need the arXiv ID parameter that our previous tool had. The docstring explains that this tool finds specialist information on AI using a natural language query. This helps our agent understand when to use this tool versus the web search or other tools. Inside the function, we again encode our query into a vector representation using our encoder model. This transforms the natural language query into a numerical vector just like before. Then we perform a search on our Pinecone vector index, but this time without any filters. We are telling it to give us the top 5 most relevant results from anywhere in the database and to include the metadata with each result. Finally, we format the search result using our format_rag_context function and return them. This more general RAG search tool gives our agent the ability to find the most relevant information across our entire collection of AI papers. It's perfect for when a user asks a broad question about AI concepts, or when the agent doesn't know in advance which paper might contain the answer. Together, these two RAG tools, the filtered and unfiltered versions, give our agent flexible ways to retrieve information from our vector database. The agent can either do a targeted search within a specific paper or cast a wider net across all papers, depending on what the situation calls for. Now that we have built tools to gather information from multiple sources, we need a way to compile this information into a coherent, well-structured research report. That's where our final answer generation tool comes in. This tool takes various components of research report, including introduction, research steps, main body, conclusion, and sources, and it formats them into a polished final report. This ensures that the information provided by our AI research agent not only accurate, but also presented in a clear, professional manner. Let me show you how to implement this tool. Now, let's create our final tool. This isn't a research tool like the other, but rather a tool that helps our agent format its finding into a comprehensive research report. First, we import the add tool decorator just like before. We are defining a function called final answer without specifying a name. So LangChain will use the function name as the tool name. This function takes 5 parameters. Introduction, which is a paragraph that introduces the user question and the topic. Research_steps, which is the steps our agent took to find the information, which can be either a string or a list. Main_body, which is the bulk of the answer containing the most important information. Conclusion, which is a summary of the findings. Sources is the references to where the information came from, which can also be a string or a list. The docstring explains that this tool returns a natural language response in the form of a research report. It details what each parameter is for and what the tool returns. Inside the function, we first check if research steps is a list. If it is, we convert it to a string by joining all the items with new lines and adding bullet points. We do the same thing for the sources parameter. This gives us flexibility. Our agent can pass in either pre-formatted text or a list of items, and our tool will handle it correctly. Finally, we construct the research report by combining all these elements into a nicely formatted string using an F string. The report has a clear sections for the introduction, research steps, main body, conclusion, and sources. This tool is crucial because it ensures that our agent's responses are consistently structured and professional. Rather than just dumping raw information, our agent will present its finding in a well-organized report that's easy for users to read and understand. In a sense, this tool acts as a template system that enforces a standard format for all of our agent's research outputs, making the agent appear more professional and its reports more useful. Now we have built our tools, we need to build the brain of our research agent, which is the large language model that will decide which tool to use and when to use it. We call this component the Navigator because it is the intelligent decision making at the heart of our system. The Navigator will take the user query, decide which tool to use, and then compile this information into a final coherent answer. Let me show you how to build the Navigator using OpenAI's powerful GPT-4o model. Now we are going to create what I'm calling the Navigator, the intelligent decision making at the heart of our research agent. This is the component that will decide which tool to use based on the user query. First, we import two key classes from langchain_core.prompt, chat prompt template and message placeholder. These will help us structure the conversation between the user and our agent. Next, we define a system prompt. This is a critical part of our system because it tells the LLM how to behave and what it is role. Our system prompt establishes that the model is the navigator, the great AI decision maker, and explain its job to decide which tools to use based on the user query. The system prompt also includes some important rules. Don't use the same tool with the same query more than once, and don't use any tool more than twice. This prevents our agent from getting stuck in loops or relying too heavily on a single tool. We also instruct the navigator to collect information from diverse sources before providing an answer. And once it has enough information to use the final _answer tool we just created. After defining the system prompt, we create a chat prompt template that structures the entire conversation. This template includes 4 components. First, the system prompt that defines the navigator's role. Second, a message placeholder for a chat history, which allows our agent to remember previous interactions. Third, the user's input, which gets inserted dynamically. And finally, the assistant scratchpad, which tracks which tools has been used and what information has been gathered. This template creates a structured conversation flow that guides the large language model in how to process user queries and decide which tools to use. The navigator will read this prompt, understand its role, examine the user's query and the current state of research, and make intelligent decisions about what to do next. This approach gives our agent a clear understanding of its purpose and constraint, helping it make better decisions about how to gather and synthesize information for the user. Now we are ready to initialize our Navigator large language model and connect all the pieces together. This is where everything comes together to create our intelligent research agent. First, we import the necessary classes from the LangChain libraries. We need tool call and tool message for handling tool interactions, and chat OpenAI for creating our language model. Then we initialize our language model using OpenAI's GPT-4o, which is a powerful model with strong reasoning capabilities. We are retrieving the API key from environment variables, which is a secure way to handle sensitive information. Notice that we set the temperature to 0. This means our model will be very focused and deterministic, minimizing randomness in its outputs. This is important for a research agent that needs to be reliable. Next, we define the list of tools available to our navigator. These are all the tools we have created so far: the two RAG search tools, the arXiv fetching tool, and the web search tool, and the final answer formatting tool. These tools gives our navigator the ability to access different sources of information and complete the results. Then we define a helper function called create_scratchpad that processes the intermediate steps of our agent's reasoning. For each action the agent takes, it adds a log entry showing which tool was used, what input was provided, and what the output was. This creates a transparent record of the research process that both the user and the agent can refer to. Finally, we define our navigator's decision-making pipeline. This is a chain of operations that takes the user input and chat history, create a scratchpad from the intermediate steps, feed all this into our prompt template, passes the formatted prompt to our large language model, and finally binds our tools to the large language model, allowing it to choose and use any of them. The pipeline structure is elegant and flexible, allowing each component to focus on its specific role while working together seamlessly. What we have built here is essentially the brain of our research agent, a system that can understand user queries, decide which tools to use to gather information, track its progress, and ultimately compile everything into a comprehensive answer. This navigator is what makes our agent truly intelligent, rather than just a collection of separate tools. Now comes the exciting part: testing our navigator and see it in action. We will provide a sample query and then observe how the navigator chooses which tools and provide an answer. This is where we start to see the power of our research agent as it navigates through multiple sources of information to provide a comprehensive answer. Now let's put our research agent to the test with several different queries to see how it handles different types of information needs. For our first test, we will use the query "What is the arXiv paper with the ID 2407.21783?" This is a perfect test case because it requires our agent to use the arXiv tool we built. Let me set up the input dictionary with 3 key pieces of information: input, which is our first test query, chat_history, an empty list since this is the start of our conversation, intermediate_steps is another empty list that will store the steps our agent takes. Then we invoke our navigator with these input. This is where the magic happens. Our navigator will read the query, decide which tools to use, call those tools with the relevant parameters, and process the information until it can provide a comprehensive answer. When we run this code with the arXiv paper query, our agent will likely use fetch_arXiv tool to retrieve the paper abstract, possibly use the RAG_search filter tool for more specific information, and then compile everything into a well-structured response. To display the name of the tool, we run the following command. It's fetch_arXiv. And to display the tool's argument, we run the following command. It's arXiv_ID, which is the article that we asked the navigator about. Now let's try another search query. Instead of this, I'm going to ask it about who won the Super Bowl 2024. Let's run the console now. Let's check the tool calls, which tool was used. It's the web search. It used the web search, which is excellent. And the argument is the query Super Bowl 2024 winner. One last query to test it. Tell me something interesting about dynamic backtracking AI and large language models. Let's run the code cell again. Let's see which tool it used. It used RAG_search, excellent. And let's display the tool's argument. Excellent, dynamic backtracking AI. This means our navigator is working perfectly. Now that we have verified our navigator works correctly, let's build a complete decision-making pipeline using LangGraph. This will allow our agent to use multiple tools in sequence and gather information from multiple sources before providing a final answer. LangGraph is a powerful library that allows us to define the flow of our research agent decision-making process as a directed graph. Each node in the graph represents a step in the process, and the edges define the possible transition between steps. Let's see how to implement this decision-making pipeline. Alright, now we are building the decision-making pipeline that will coordinate our agent's workflow. This is how our tools will work together in sequence. First, we define the run navigator function. This function invokes our navigator with the current state, extracts which tool it decided to use and what argument to pass, and creates an agent action object to record this decision. The log is marked as TBD since we haven't run the tool yet. Next, we have the router information. This examines the current state and determines which tool to use next based on what the navigator decided. It's a simple function that extracts the tool name from the most recent step. We then create a dictionary called tool_str_2_ function that maps the string names of our tools to the actual function objects. This allows us to look up and call the right function based on its name. Finally, we define the run tool function. This takes the current state, extract which tool to use and what arguments to provide. Call that tool with those arguments and create a new agent action with the tool's output recorded in the log. Together, these functions create a pipeline where our navigator decided what to do. The router ensures the right tool is selected, and run tool executes that tool and captures its output. This cycle repeats until our agent has gathered enough information to provide a final answer. This approach gives us a flexible workflow that can adapt to different types of queries by selecting and combining tools in the most appropriate way. Now let's define the structure of our agent state using type dict. This gives us type safety and makes our code more robust. We are importing type dict, annotated, and list from typing module to create strongly typed structures. We are also importing agent action and base message from the LangChain_core libraries, which we will use to track our agent's actions and conversation history. The agent state class defines exactly what information our agent needs to keep track of. First, input, which is the user query as a string. Second, chat history, which is a list of messages exchanged between the user and the agent. And finally, intermediate steps. This tracks the sequence of tools used and their outputs. Notice the special annotated type of intermediate steps. This uses operator.add to specify that these steps should be combined when the state is updated. This allows our state to accumulate the result of multiple tool calls. This structure ensures that all parts of our system have a consistent understanding of what the agent knows at a given time. It's like creating a standardized format for the agent's memory, making it easier to update and access information throughout the research process. Now we are creating our decision-making graph using LangGraph, which will orchestrate the entire flow of our agent. First, we import state graph and end from langgraph.graph. State graph will help us build a flowchart-like structure for our agent's decision process. We initialize a new state graph using our agent state type, ensuring type safety throughout the workflow. Next, we add nodes to our graph. Each node represents a function that our agent can execute. Navigator node will run our Navigator LLM to decide which tool to use. We also add nodes for each of our tools: RAG_search_filter, RAG search, fetch archive, web search, and final answer. We set Navigator as our entry point. This is where execution always begins. Then we add conditional edges using the router function. This tells the graph where to go next based on the Navigator decision. For each tool except final answer, we add an edge back to the Navigator. This creates a loop where after using a tool, the agent returns to the Navigator to decide what to do next. Finally, we add an edge from the final answer to end, which tells the graph to terminate execution once the final answer is generated. The last step is compiling our graph into a runnable object that we can execute with user queries. This graph structure gives our agent a clear workflow: decide which tool to use the tool, evaluate the result, and either gather more information or provide a final answer. It's like creating a flowchart for our agent to follow when researching any topic. Let's visualize our decision-making graph to better understand the workflow we have created. We are importing image and display from ipython.display, which are tools that help us show images in our notebook. With this single line of code, we are generating and displaying a visual representation of our agent's workflow graph. The runnable.getGraph method retrieves our graph structure and raw mermaid PNG converted into a PNG image using the mermaid diagramming format. When we run this code, we will see a flowchart that shows exactly how our agent makes decisions. The diagram displays our navigator as the starting point, each tool as a separate node, arrows showing how information flows between components, the conditional paths that determine which tool gets used when. This visualization is incredibly helpful for understanding how all the pieces fit together. It shows how the navigator directs traffic to different tools, how those tools feed information back to the navigator, and how eventually the final answer tool produces our output. Visualizing complex systems like this is a best practice in AI development. It helps us verify that our design matches our intentions and makes it easier to explain the system to others. Now let's put our entire system to test with a real query. We are invoking our compiled graph with a specific input. Tell me something interesting about dynamic backtracking AI and LLMs. This is a query that will require our agent to access specialized AI knowledge. We are providing an initial state with the user query and empty chat history. Once we run this code, our agent will follow the workflow we designed. The navigator will analyze the query and decide which tool to use first. That tool will be executed to gather information. Control will return to the navigator, which will decide what to do next. Then this process will continue until the navigator decides we have enough information. Finally, the agent will use the final answer tool to compile a comprehensive response. And great news, our research agent is working perfectly. First, you can see our navigator starting up with empty intermediate steps, then deciding to use the RAG search tool to find information about dynamic backtracking AI. The tool successfully returns information from academic papers about dynamic backtracking. Next, our navigator decides to search for information about LLMs, again using the RAG search tool. This demonstrates how the navigator is intelligently gathering information from multiple angles related to our query. Then it switches to the web search tool for post topics, showing how it's combining specialized academic knowledge from our vector database with general knowledge from the web. Finally, after gathering sufficient information from multiple sources, it uses the final answer tool to compile everything into a well-structured research report with an introduction, research step, main body, conclusion, and sources. This is exactly what we designed our system to do: make intelligent decisions about which tools to use, gather information from diverse sources, and present it in a coherent format, even with some component not working perfectly. The core architecture and decision-making flow is functioning as intended. This demonstrates the robustness of our agent-based approach and the power of the LangGraph framework for creating intelligent research systems. The final piece of our research agent is the ability to generate well-formatted, comprehensive report from the information gathered. This ensures that the information is presented in a clear, professional manner that's easy for the user to understand. Let's build a function that generates this structured report from the navigator output. Finally, let's create a helper function to format our agent's output into a nice-looking report. This function takes the dictionary output from our agent and transforms it into a readable document with clear sections. First, we check if research step is provided as a list. If it is, we convert it to a string with bullet points. We do the same for sources. This gives our agent flexibility to provide these sections in either format. Then we use an f-string to create a well-formatted report with clear section headers: introduction, research steps, report, conclusion, and sources. Each section is neatly separated with a header and divider for better readability. This formatting function is the final touch that ensures our agent's output is presented professionally. When users receive responses, they will get a structured research report rather than just raw information, making the agent's finding much more valuable and accessible. Now let's test our entire research agent system with a specific query about an arXiv paper. We will ask it to create a summary about the paper with ID 2502.20384. We invoke our runnable graph with the query and an empty chat history. This starts the entire process. Our navigator will determine which tool to use, gather information about this paper, and compile a research report. After the agent completes its work, we extract the final output from the last tool that was used. Since our final tool is always final answer, we can get its input from the last item in intermediate steps. We then pass this output to our build report function, which format everything into a clean professional document. Finally, we print the report to see the result. Let's run the code cell now. And amazing! Our agent runs successfully. The printed output shows us the introduction, research steps, main body, conclusion, and sources, all neatly formatted in sections. This demonstrates the complete workflow of our research agent, from receiving a query all the way to producing a well-structured report. Users can now ask about specific papers and receive comprehensive, readable summaries without having to do the research themselves. And there you have it. We have built a powerful AI research agent that can search through academic papers, fetch data from arXiv, research the web, and generate comprehensive research reports. In this episode, we have built a specialized tools for our agent to access information from different sources, created a decision-making system using LangGraph, and developed a report generation framework. Our agent is now capable of answering complex questions by drawing on multiple sources of knowledge. In our next episode, we will focus on enhancing our agent with additional capabilities and make it even more user-friendly. We will explore how to enhance its performance and answer more complex types of queries. I hope you enjoyed this episode and learned something valuable. If you did, please give it a like, subscribe to my channel, and ring the notification bell. Thanks for watching, and I will see you in the next one.